Okay, all right, so indirect measurement. What indirect measurement is, okay? If you were to do something indirectly, you're kind of going around something. Does that make sense? Okay. If I wanted to, a lot of times they talk about direct flights, okay? If I want to go from, let's say Detroit to Venice, Italy, okay? Or let's go Milan. I don't know if Venice has an airport. Probably not. It's all water, right? Okay. So say I want to go to Milan, right? A direct flight, I leave Detroit, and when I land, I'm in Milan, right? An indirect flight might take me from Detroit to Houston, to LA, then to Milan. Does that make sense? I got there indirectly, not through a direct route, okay? So the same idea when we talk about measurement. We're getting to a measurement that we're interested in, going through the use of other values, okay? Other measurements that are maybe a little bit easier to attain. One of them, one procedure for using indirect measurement or determining some indirect measurements is the use of a mirror and understanding physics a little bit. Okay. Now I might use the wrong word here from the physics aspect, but you guys have all played pool before, right?
Yes.
You play that game. You play pool on your computers, right?
No.
All right.
Okay.
If I have a pool ball and I want to bounce it off the rail, okay? I'm going to hit it here. Man, I'm going to bounce it off the rail there. When it hits the rail, okay, we call this in physics an angle of incidence. Okay. An incident is when something happens, right? Okay. So at that point, our pool ball is intersecting the rail. Okay, we call that the angle of incidence. The angle of, not sure whether it's reflection or deflection here, that the pool ball leaves the rail. What is the argument between the angle of incidence and this angle here? Yes, it's the same. And that's a physical property that we know from physics. Okay? If I'm taking like tennis balls or baseballs or whatever, and I'm bouncing them off the gym floor, or a basketball, I bounce past to somebody. The angle of the ball leaves the floor is the same as the angle of the ball when it makes contact with the floor. Okay? And that happens with, pool balls, basketballs, all that kind of stuff. But it also happens with light. Okay? And now when we talk about it happening with light, the way that we're going to be able to determine these angles that the light is kind of bouncing off of something is to use a mirror. Okay? Because then when the light bounces off the mirror, and that light is redirected towards my eyes, that's what allows me to see the object in the mirror. Okay? So there's a lot of physics and a lot of things that you'll understand on how light travels and how we perceive light and that kind of stuff later on in those courses. But we can use this logic, this physics that maybe we have no understanding about to find a measurement pretty easily. Okay? So we've got here, that's J, S is down here, V, T, and H. What happens is this guy stood at the base of the cliff, right at S. And he started walking away from the cliff. Now, he just walked an arbitrary distance. Doesn't matter. He walked 34 feet. Okay? And he dropped a mirror on the ground. All right? And then when he was standing right above that mirror, he could only see blue sky. Can't see anything other than that. He's right above it, right? Does that make sense? All right, so he starts walking away from that mirror. Okay? And eventually, as he's looking at that mirror and he's walking away, eventually the cliff, because of the angle of light that's coming off of that mirror, gets redirected into his eyes. Eventually, the cliff is going to be visible in the mirror. Does that make sense? Yeah. At that point, he stops. Okay, so that's point T there, where he's standing. When that happens, when he's able to see the top of the cliff in the mirror, we've got this angle here and that angle there. This is the angle of incidence. Okay, the angle that the light is entering the mirror, and this is the angle that the light is leaving the mirror, right? And it's going into his eyes, so that's what's allowing him to perceive the picture. Okay, but what do you know about those two angles? They're the same. What do you know about that angle there and that angle there?
They're right angles.
They're right angles. So these two triangles are both right triangles that have another angle congruent, right? So these two triangles are similar, aren't they? Does that make sense, everybody? Okay. So I'm going to write a similarity statement here. I'm going to say that triangle, let's go JVS. Triangle JVS is similar to triangle HVT. Do you guys agree with that? Okay. And then from that, I can say JS, which is that distance there. JS should compare to HT, wouldn't it? And then S to V or V to S should be comparing to VT. Does that argument make sense to everybody? Okay. Now the reason I'm saying I could also make the argument that H to V and J to V are the same, but I don't know those values, so I'm not going to create that ratio. But the reason I do that is because now if I look at these, is this the height of the cliff, J to S? Is that the height of the man?
Yes.
All right, so compare the heights of the cliff to the height of the man. Is this the distance from the cliff to the mirror?
Yes.
And this is the distance from the man to the mirror, right? So there's a link there between those two. This being 34, and this being 6, right?
Yes.
Okay. The numerators came from the same triangle. They came from the big triangle. The denominators came from the small triangle. But now, using this physical property and understanding how light reflects off of mirrors, can allow us to find that height of the cliff by cross-multiplying, knowing exactly how high that cliff is without ever having to measure the cliff directly. Does that make sense? And nowhere in this problem did I ever get to the top of the cliff and measure straight down. Okay? So you guys, I'll leave the cross-multiplication up to you, but you should be able to do that and solve for x and determine the height. Is that all right? Okay. There's a lot of things in real life that we like to use kind of that property. There's a lot of things, especially right now, you guys are in kind of interesting time frame in world history in which we're trying to send people to other planets, right? Okay. And we want to know as much about those other planets as we can before we send people there, right? We know dimensions of certain objects on those planets, okay? Certain maybe geological structures and stuff like that, the dimensions based off of physical ideas like this, indirect measurement concepts like this, okay? So that's one thing that we can do with indirect measurement and similar triangles. Another one that you're going to see is this idea, okay? Using shadows and how one person's shadow or one object's shadow then relates to another shaped shadow or another person's shadow. And we can use the fact that we get similar triangles when we draw a picture here to allow us to measure the height or length of a shadow of some object. Okay? What I want you to understand is that when we do these, you have to measure the shadows relatively close to one another in regards to the time span. Okay? I don't want to measure the shadow. Let's say I'm using my shadow to approximate the height of the Washington Monument. I would not measure my shadow at 10:30 a.m. and then measure the height or the shadow of the Washington Monument at 6 p.m. Okay, because we no longer have the idea of similar triangles. Okay, if I measure my shadow at 12 p.m., I better measure the Washington Monument at the same time. Okay, now that might be kind of infeasible for us to do. Okay, if we're by ourselves. But just the size of the distance basically from us to the sun would allow us to have the sun rotate or have Earth rotates around the sun. We could probably maybe do it within 15 minutes of one another. Does that make sense? If I had like a classroom exercise, we went out in the courtyard and did this, we would want to do it quickly and not lag a lot of time because your measurements become different than if you let a lot of time elapse between your measurements. So that's just something to understand about kind of the angle of elevation that we get from the sun. But this is the concept. And got this in there from last class. We've got this situation says a building casts a 103-foot shadow at the same time that a 32-foot flagpole casts a 34.5-foot shadow. It says how tall is the building to the nearest 10th. Okay. So right now, right here is my building. Okay. And I don't know how tall it is. That's what they're asking me for. Okay. But the sun up here okay, is casting light, right? Okay. And that light is then being blocked out by this building and creating our shadow down here, right? Does that make sense to everybody? Okay. Well, the angle that light comes in and touches our building or hits our building is the same angle that it comes in and touches our flagpole here. Okay. So, what I want you guys to understand is either view it as that angle there compared to eventually that angle there. Or, in a couple chapters, we'll talk about how that angle and that angle maybe be easier to view and visualize and think about. But those red angles would be congruent. We also know that that angle and that angle are both right angles, right? That's kind of the assumption that we make, that when somebody put this flagpole in, they had a level with them, they tried to make it vertical, that kind of stuff, right? Are those two triangles similar? Yeah, okay. They got angle in them, okay, whichever set of angles you want to look at. We're trying to find the height of the building, and the shadow that it cast was 103 feet. So that's that shadow right there. The flagpole at the same time casted a 34.5 foot shadow. But we know, I don't know what's going on there. We know that the flagpole had a height of 32 feet, isn't it? Okay. Now everything's in feet, so this is good. Should I be able to compare the building's height to the flagpole's height? That kind of makes sense? Hopefully you understand that logically that would be how we would name it. If I go like A, B, C, and then D, E, F, you can call this triangle ABC on the left. So A matched up to D. B was the right angle, so that's going to be E and F. And now if I compare AB needs to be compared to DE, and that's what we've done, X to 32. All right, then CB, these last two letters need to be compared to EF. Well, CB is the building shadow. EF is the flagpole shadow. Okay, so there are times where you might want to use that similarity statement, but there's also situations, to understand the context of the problem, you compare a shadow to a shadow. You compare a height of an object to a height of an object. Does that make sense? Okay, so maybe you don't necessarily need a similarity statement, but it does allow you to set up that proportion. Can we now cross multiply? Cross multiply solve for x. You will then know the height of that building, and you never have to physically measure the height of the building. Okay, 32 feet for flagpole might be a specification that we know because that's the type of flagpole we bought. Okay. We can measure off that 34.5 feet pretty easily on the ground. We measure the 103 feet pretty easy on the ground. So they're accessible, attainable values that allow you to measure the height of that building, which might not be an accessible or attainable value. Okay? And depending on how accurate, this kind of get into your chemistry stuff, your science things, and all kind of things. Depending on how accurate our device was that we used, or how precise it was, to measure EF and BC, okay, and DE, will then tell us how accurate our actual value or actual height of the building is through that calculation. Is that all right? So that's, you see a lot of these questions. Math Excel, for some reason, likes these shadow questions. It's a lot of their story problems, but it's one application. It's a physics concept with the light, creating shadows and that kind of stuff, but we can explain it with similar triangles. Let's get to this one. Okay. I want to show you, just kind of walk you through this picture, because the reason I'm explaining this stuff to you is because some of your homework questions are going to, you're going to read the story problem, and they're going to kind of take for granted that you understand the physics of what's happening. Okay. So some of these story problems here that we do today should kind of mimic or be somewhat similar to what you see in your homework. It says, Peter takes a picture of Wendy during a vacation. Wendy is 158 centimeters tall and is 2.4 meters away from the camera lens. The film is 4 centimeters from the lens. How tall is her image on the film to the nearest tenth of a centimeter. All right, so this is what I want you guys to kind of understand. And again, there's a lot of like physics that has to go into this with like light and stuff like that. But I want to pull up a picture real quick of the internals of a camera that has film in it. Okay. So let's see if I can get a good one here. All right, let's kind of look at this here. So here's inside the insides of a camera. Okay, so this is kind of the like a bird's eye view or a cross cut of a camera like this one here or this one here, but it's being cut kind of that way, horizontally. Does that make sense? Okay, and looking straight down on it. You've got your lens here, and light's passing through that lens, and there's a lot of mirrors and other lenses inside here that take the light, bounce it off, but then it's going to redirect it on a film. So over here is our film, okay? The argument here is that our film, as we read this, they're going to say our film is a certain distance from the lens, okay? And then the object that we're viewing over here is a certain distance on the outside of the camera from the lens. Is that all right with everybody? Okay. So I'm going to draw a picture that kind of mimics this. If I've got, let's just say, it's not the greatest, it's not going to be the greatest picture, but let's just say that this is our lens. Light is going to be coming through that lens, kind of in that nature. Okay, and actually, yeah. And over here, these rays of light are basically allowing us to see the actual person. Okay, and Wendy is going to be over here. Wendy is going to be 158 centimeters tall. Okay. She's this. So the camera, you know, all of the internals of the camera on this side. Okay. So on the inside of the camera, you'd have your two spools here, and you've got film wrapped around those two spools, and this light is being redirected to that film. Does that make sense to everybody? Okay. They're telling us that that film is 4 centimeters from the lens, and they're telling us that Wendy over here is 2.4 meters from the film. Is that all right with everyone? Okay. So now looking at this, what we've got, and I'm gonna kind of highlight the right triangles that are created here. We've got this right triangle, and we have that right triangle. Would you agree with that? Okay, because distance has to be measured from a point perpendicular to a side, or to a segment. They want to know how tall is this girl on the film. So maybe that distance right there. Okay. If I'm doing this, would you agree that that angle right there and that angle right there are the same? They're vertical, aren't they? With the dotted lines? Well, if I cut that one in half and cut that one in half, are those halves still the same? We got a right angle here, we got a right angle here, and we got a right angle here. Okay, so those angles along with these two, we've got angle going on. So what I want to show you here is that this whole setup of where this girl is and how her image is then placed on the film inside the camera is due to similarity. Okay, and we can then use these similar triangles to know how big she is on the film. Okay. Would you guys agree that this 158 should relate to the size that she is on the film. She's 158 centimeters tall. She's X centimeters tall on the film. Is that okay? This 2.4 meters is how far she is away from the lens in actuality, in real life. All right, and this 4 centimeters is how far she is away from the lens inside the camera on the film. Is that okay with everybody? That's kind of how you would set that proportion up. Okay. Now I don't know enough about cameras and all that kind of stuff to know that image and that explanation is 100% accurate. It's pretty close to being correct. I want to get these things to get out of the way. But if you know anything about, is anybody like interested in photography or know anything about photography, take pictures or anything? There's an extreme, extensive amount of math involved in photography and doing like shutter speed and aperture and that kind of stuff. Distances between lenses and focal lengths and stuff like that. A lot of math involved in it, but a lot of it uses similarity and proportions to allow images to be displayed on film. We can cross multiply now, but if I cross multiply now, I would get something that is completely wrong. Why would I get something that's completely wrong here if I cross multiplied right now? Good. Okay, I've got different units here, right? I got centimeters here and I got meters over here, correct? So what I need to do is change everything into one or the other, right? Now it's a good idea to look at the question and see what the question is asking for. They want the answer in centimeters, right? So does it make sense to change everything into centimeters? Yeah. So I got 2.4 meters. How many centimeters are there in a meter? 100. So I got 2.4 100s, right? So is that another way of saying 240? All right, so we got 240 centimeters. Now I can cross multiply and get 240x is equal to whatever 158 times 4 is. And then my answer then will be in the units of centimeters. And I believe it ends up being like 2.63 if you do that correctly. Just double check that. $158 times 4 divided by 240. 2.63. Okay, and that argument makes sense, right? She's 4 centimeters away from the lens, so on the picture she should be pretty small, right? If you would not have changed things into centimeters, we left it as 2.4. Kind of look what happens. If I would have left it as 2.4, I would have had Are we gotten that number, right?
Yeah.
Is it still the same 26333333333?
Yes.
The decimal point is just in the wrong spot, right?
Yeah.
And that has to do with the fact that the metric system is essentially powers of tens from one unit to the next, right? Okay. So when you are using or addressing questions that use the metric system and you get the answer wrong, your argument is like, well, I got the same numbers, I just got the decimal place in the wrong spot. That's an issue, okay? So having 2.6333 is different than 263.3333, okay? But if you get that, if you know that we're going through things and you're getting the same numerical quantities, it's just the decimal place is shifted, and that tells you you messed up your units. You didn't convert units over. Does that make sense to everybody? Do you guys know from science class this
Yeah. King Henry died by drinking chocolate milk. Chocolate.
Okay, so K stands for
Kilograms.
Okay, well, careful, because you could be in your base unit of meters, grams, or liters, right? Okay, so it's kilo, whatever one of these. So kilometers, kilograms, or kiloliters. This is hecta, right?
Yeah.
Okay. This is deca. And this is deci. This sometimes I'll put this DA and then DI. Okay. To the right is deci. To the left is deca. This is centi and this is milli, right? Okay. Now there's other parts. There you can go beyond kilo and you can go beyond milli. Okay. But those are the ones that we use the most. And if I'm right now at 2.4 meters, you basically put yourself at that unit. Okay, so I'm at meters, and I want to go to centimeters. So to go to from the base to centimeters, you go 2 spots, right? So that means my decimal needs to go 2 spots, and it puts in another 0. And it gets me to centimeters. Okay, so that's a dimensional slider. It allows us to slide our decimal place appropriately. You do not have one of those for systems that do not have a common base. Okay, the metric system has a common base of 10, right? Okay, this is 10 to the first, 10 to the second, 10 to the third. As we move along that, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, as we move to the left, or sorry, to the right, and then positive to the left. You can't do that with the English system, okay? Because it's in multiples of 12 or multiples of 60 or multiples of non-10 base. Does that make sense? Mm-hmm. Okay. There are values that allow us to go from, the English system of feet, miles, that kind of stuff, pounds, over to kilograms or centimeters or meters, and we'll do some of that stuff as we move on throughout the year. But that is going to be something that you use tonight on your homework. There are some questions that actually convert to meters, centimeters, and that kind of stuff. Okay, but you're going to use similar triangles. Read the story problems. Use similar triangles. Draw pictures to organize your thoughts. Okay, and I think for the most part, they provide you with all the pictures you need, but you might have to add some components to them to really recognize your similar triangles.